Welcome back, everyone. In this video, I will be continuing the chain rule lecture. Now, I have 4 questions left, where there's 6 total. I'm not sure if we'll get through all 4 on this because I want to go ahead and make sure we do it slowly, make sure you can really take in what's going on. And, a big thing about this next section or the next couple problems, as you're going to see, is it's not just the chain rule. It's going to be involving the power rule, the quotient rule, the product rule, e to the x, trig derivatives, pretty much anything that we've done already. All right, so what I want to go ahead and do is just exactly that. Jump into number 3. We want to find dy over dt if y equals 3 times t cubed plus 4 to the 4th power, and then times sine of 2 pi t. Now, one thing I'm going to notice here right away is, yes, I'm going to use the chain rule because I have something raised to the 4th power that's not just t, and I have something inside the sign that's not just t as well. But what I can't do is disregard what I need to do first. And the first thing I need to do is the product rule. Why? No matter what is really going on in the function, we're having a product here. We're multiplying this first thing, 3 times t cubed plus 4 to the 1st power. 4th power is our first, and it's multiplying the second thing, sine of 2 pi t. Okay, so we have to use the product rule. And just like with the product rule, if you have a multiplication, you're going to use the product rule. If you have a division, you're going to use the quotient rule. But just depending on the way the problem is set up, you might do the chain rule first. You might do the product or quotient rule first, depending on how it's written. This one, the multiplication is outside of the chain rule part. So the chain rule part, we can do this individually. We don't have to do them together, more or less. All right, so let's just see how it works. What you're going to notice here, hopefully, is that it really doesn't work any differently. The product rule says what? We do the derivative of the first, so dy over dt of the first, 4, times the second, plus the first, times the derivative of the second. And now you'll see what I mean. When we write down the product rule, because we have this multiplication on the outside, if there was a huge power around this, I'll erase it, but if there was a huge power, to the 4th power, but the idea is if there was a big power to the entire thing, then what would happen is this would be the inside, and x to the 4th or t to the 4th would be the outside, and we'd have to use the chain rule first. But because that's not there, I just have a product, and the product rule tells me to do this. Now is when we would use the chain rule, because we have to compute these 2 derivatives. And in these derivatives, like we described before, it's something we have to use the chain rule for. So because I'm going to have to use the chain rule here, I know we usually do them in line, and when you get more comfortable with the chain rule, I would just go ahead and do that. But at this point, it might be better to work it on the side. Sort of like when we did the product rule with 3 products, we worked the extra product rule on the side and plugged in. So let's go ahead and work this on the side. We want to do the derivative of 3 times t cubed plus 4 to the 4th power. Right, and this might be the time where you really think back to the very first derivative rules. So how do we want to do this? This is definitely not a product because we just have a 3 here. If it was 3t, then this would be terrible because then we'd have to do another product rule and so on. But we can move the 3 out, and we haven't visually written that in a while, but let's just go ahead and do that. Maybe it'll help us see more easily what we need to do, how we're going to do this derivative. So we got 3 times d over dt, and we want to do the derivative of t cubed plus 4 to the 4th power. Right, so I got my 3 out front. Multiplication. How am I going to do the derivative of t cubed plus 4 to the 4th power? Well, this one's a lot like number 2 that we did in the previous video. If you think about this being the inside, which it is, t cubed plus 4, then what we're having with the outside is it's like t to the 4th power. Replace this with t, and then that's something we use the power rule for. We bring the 4 down, we rewrite the inside, and then we subtract 1 from the power. And one thing I would recommend, especially if I'm saying things that are really clicking, but you think, how am I going to remember that? How am I going to do that? Maybe just write in your own notes exactly what I just said. You know, this is really, we want to think about this as just t for a second, and we use the normal power rule, bring the 4 down, subtract 1 from the exponent, and then rewrite the inside. Okay. But then the extra chain rule step says do the derivative of the inside. We have the derivative with respect to t of t cubed plus 4. And what is the derivative of t cubed plus 4? That's 3t squared plus 0, which is just 3t squared. Okay, so we have 3 times 4 is 12. We have t cubed plus 4 to the 3rd power. And then, as we just established, this is 3t squared. And you can simplify it a little bit more, which we might as well. 3 times 12 is 36. We got t squared. And then we got t cubed plus 4 cubed. Okay. All right, so we've got our first derivative in there simplified. I would say this is definitely the more challenging one. The other one should be a little simpler. Maybe based on the first example that we did with the cosine, you can pause the video and try to do the derivative of this one and see if you come up with the same answer. What is the derivative with respect to t of sine of 2 pi t? Well, the outside function is sine. What's the derivative of sine? It's cosine. We leave the inside the same, 2 pi t. And then we multiply by the derivative of the inside, the derivative of 2 pi t. And the derivative of 2 pi t is just 2 pi. So this is cosine of 2 pi t times 2 pi. And if you want, you can rearrange it and put the 2 pi in front. We got 2 pi cosine of 2 pi t. Okay. Now we got each of our derivatives to plug in. We're going to plug in, and maybe it looks like it'll simplify when we do it. Maybe it won't. We'll see. But after we plug in, we'll pretty much be done. The first one, the derivative here, we got 36t squared times t cubed plus 4. What I have boxed in orange, cubed. And then that's multiplying sine of 2 pi t. Then we have plus 3 times t cubed plus 4 to the 4th. And then we multiply by the derivative of this, which was 2 pi cosine of 2 pi t. Now this isn't going to simplify a terribly large amount. In fact, I wouldn't try to do too much, but there is one thing I would definitely factor out. And we have a t cubed plus 4 cubed and a t cubed plus 4 to the 4th. Whenever you have the same factor in both terms, you can factor out the smaller of the powers. So we can take out a t cubed plus 4 cubed from each. You may also notice that we have actually a 6 in common because we have 36 here, and 2 times 3 is 6. But I'm not going to worry about that. I'm just going to worry about factoring this out. We take out the t cubed plus 4 cubed. When I take that out, this entire portion's gone from the first part, so I have 36t squared times sine of 2 pi t. And in the second part, what am I left with? I am left with 3. I have one of the t cubed plus 4s left. And then I have the 2 pi. So maybe I can just go ahead and do 3 times 2 pi is 6 pi and put that in the front here. I have one of the t cubes plus 4 left, and then I do times the cosine of 2 pi t. Now, because of the rest, aside from factoring out the 6, you're not going to really try to factor out anything. This is sine, this is cosine, they have nothing in common. We have a t squared here, we don't have a t squared here. So really, this is plenty far. But very often, especially when you do the product and quotient rules with the chain rule, is you'll get something that factors out at the end. Not always, but often. And that's usually good to go. But I know I have a couple other things boxed in, so let's go ahead and box in. That is the answer. Don't know why I pluralized it. All right, so that's an example of the product rule popping up with the chain rule. Number 4 here, and number 5, if you're already peeping down, both are going to interact the chain rule with the quotient rule because they both have divisions in them. All right, so how are we going to do number 4? You see the division here, right? Because it's written in the exponent, it can look really weird, but the exponent here, we have e, and it's raised to the tangent of z divided by z power. How are we going to do the derivative of that? We see division, we want to use the quotient rule, but it's also not just e raised to z, right? We know we could do the derivative if it was just e raised to the z, because that would be e raised to the z, but we have to do the chain rule as well. Well, in this one, because the exponent is what we're focused on, it's pretty much the inside part, our outside part is the e, we're going to have to use the chain rule first. Okay, so just to explain why I'm using the chain rule first, if this thing was just z, don't worry, I'll erase that, then I could do the derivative. What's stopping me from doing it directly is that the exponent, which is the inside, we think of the exponent as the inside when we're talking about exponential functions. Because that isn't just z, I have to do the chain rule first. The inside is what is not working for us correctly. Okay, so just a little comment here with exponential functions, the exponent in exponential functions is the inside. Some people actually go so far as exponential functions are so common, especially e to the x, that they actually write e to the x as exponent of x. So they write it to make it look like the exponent's actually on the inside. Now this isn't very common, and especially at this point in math, so I'm not going to start introducing that right away. But if you ever use a calculator, or if you're ever reading something that says exp with parentheses around it, it's actually e to the x as well. All right, so how are we going to do this? Like I said, we're going to do the chain rule first. Y prime, derivative of the outside. The outside is just the e to the z part. Right, just like when we did the previous problems, we talked about the outside here was really x to the third power, because we were thinking about replacing the entire inside with x, and the outside here was just really cosine of theta. But just the same idea. If we thought of replacing the entire exponent with just z, then we would have e to the z. The derivative of that is itself, but we leave the exponent the same because that's the inside. So the derivative of e to the z is e to the z, but in place of z for the exponent, we keep our same exponent, tangent of z over z. And then what do? We multiply by the derivative of the inside. We multiply by the derivative of, d over dz, not dt. I guess the t and the tangent threw me off. And we do the derivative of the exponent, tangent of z over z. Right? So once again, just to reiterate, because it's the first exponential one we saw, the inside is thought of as the exponent, and then the outside is just exactly that. So e to the z is the outside, the inside is tangent of z over z. And if you want to write that in your own notes, feel free to do that. But once we have that figured out, it's just like the previous couple that we've started trying to do in line. We have just this part, which is just itself, e to the tangent of z over z. There's no derivative to indicated here to do because we already did the derivative of the outside. Now, the derivative of the inside, this is going to require the quotient rule. Right? It's going to require the quotient rule And to do the derivative of the inside, let's go ahead and I like to do it on the side because we've done the quotient rule quite a few times as well. And we know that that's not ever really a short task. All right, so the quotient rule says we do the derivative of the top. The derivative of tangent is secant squared of z. Keep in mind that the inside is just z here, so we can use our old rules. We don't have to use another level of the chain rule. Then we multiply by the bottom, which is just c. We subtract, we multiply the top, tangent of z, by the derivative of the bottom. The derivative of z is 1, so actually I don't have to write it, and it's over z squared. Now the question with these is always, can you simplify it? And I think I remember mentioning before, when you want to try to simplify, you only try to simplify the numerator at first, and we cannot because this thing has a z in it, and this thing does not. A z on the outside, I mean. So this isn't going to simplify, and actually all we have to do is plug this in. Keep in mind it's multiplying the side, it's not multiplying the exponent, multiplying the side. So this is times secant squared of z times z minus tangent of z over z squared. Now this is perfectly fine because there's no way to simplify this with this. This has stuff in an exponent. This is not exponential at all. But if you want, you can rewrite it in front to make it less confusing or maybe more obvious that it's not multiplying the exponent. So if we want to move this in front, that's really all I would do. Secant squared of z. If you like this z being in front of the secant squared, you can put it there because it's multiplication minus tangent of z over z squared. And this whole thing, I'll just put in parentheses to make it clear, it's multiplying e to the tangent of z over z. Either one of these last two are exactly the same and correct. It's just sometimes, or most often, people will put the e to something in the back. That way there's no ambiguity. Am I raising something else in the exponent? No, I'm not. All right. Number 5 here. Number 5 says find f prime of x if f of x equals the square root of x plus 3 over x minus 4. Once again, you should notice two things. You have to use the quotient rule, but why do we also have to use the chain rule? Well, it's the square root here. It's always good when we're doing derivatives to rewrite radicals as exponents. We've gone over that quite a few times. And the square root as an exponent is the 1/2 power. So I'm just going to rewrite this x plus 3 over x minus 4 to the 1/2 power. It's the same thing, but doing the derivative of this is a lot easier than this. What I want you to recognize here is that even though this looks a lot different than the previous one, we did the quotient rule second because of the way it worked out. You still want to focus on, am I doing the chain rule first? Am I going to do the quotient rule first? This is still going to be the chain rule first. Why? Well, it's very much related to the number 2 example above, but I'll just re-explain it here. If you think about the x plus 3 over x minus 4 being just x, and like before, when I do this, I'll erase it. The inside is being raised to the exponent. The exponent part is the outside function. That is our chain rule. Okay, so we can do x to the 1/2 and then implement the chain rule by doing the derivative of the inside after it. Okay, so once again, just don't get it in your head that when you do the product rule, because I know number 3 was the product rule with the chain rule, we did the product rule first, and 4 and 5, we did the quotient rule after the chain rule. Those are just these examples. You can mix it up. You can, anytime you interact the quotient rule or the product rule with the chain rule, one or the other can come first. You have to get a feel, you have to recognize what you're looking at. But here I just know if I replace x plus 3 over x minus 4 with x, then I can do that derivative. Just revisiting number 3, if I replace t cubed plus 4 to the 4th with just t, like I mentioned before, I still have to do the product rule. So that's how I know I'm going to do the product rule first here. But for these past two, doing the quotient rule second after the chain rule. All right, so let's go ahead and jump into it now. F prime of x. We've pretty much seen something like this before. In number 2, we just didn't have the quotient rule inside, but that's okay. We know the exponent is really the outside function. We use the power rule. Take the 1/2. Rewrite the inside, x plus 3 over x minus 4. And subtract 1 from the power. 1/2 minus 1 is negative 1/2. That might be a number you have memorized by now from doing enough practice problems. And then we multiply by the derivative of the inside, the derivative of x plus 3 over x minus 4. Right. Now we're, pretty much done. There is a couple things you want to do. Of course, we're out to do this derivative, but typically we don't like negative exponents. And when we think about negative exponents, usually we want to make them positive by bringing it down to the denominator. But when you have a fraction in here, you can make the exponent positive if you flip the fraction. So if you want to get rid of the negative exponent here, which you should, just flip the fraction inside. You get x minus 4 over x plus 3. And that's to the 1/2 power. And now, just like before, when you do the derivative of this, I would recommend, because it is the quotient rule and it's never just one quick thing, go ahead and just do it on the side and then plug it in. So the derivative with respect to x, x plus 3 over x minus 4. Do the quotient rule here. Derivative of the top is 1 times the bottom, x minus 4. Not sure why that x looks kind of weird. Minus the top, x plus 3 times the derivative of the bottom, derivative of x minus 4 is also 1, over x minus 4 squared. And now on the top, you can kind of see here that a lot's going to cancel because multiplying by 1 does nothing. So we can just get rid of the parentheses in front. There's nothing else distributing it. We have x minus 4. And the one in the back, just distribute the minus sign through. We get minus x minus 3. And then the x's cancel. X and minus x. And what are you left with? Negative 4 minus 3 is negative 7. Over x minus 4 squared. All right, and you can go ahead and now plug that in because that's what this is. We're trying to multiply this part by the derivative, and we just computed it. We get negative 7 over x minus 4 squared. Now there is a couple things you can do here. It's up to you. I honestly prefer the way it's written than what I'm going to quote unquote simplify it to, because I want you to see how you could probably get an answer that if you type this into Wolfram Alpha, do the derivative of this and check your answer, you'd probably see what I'm about to show you. All right, so first thing is that I'm definitely going to multiply the negative 7 to the 1/2. I would do that anyway, and I would get negative 7 over 2. Well, one thing that when you have an exponent with a fraction, you can distribute the exponent to the top and bottom, meaning I get x minus 4 to the 1/2 over x plus 3 to the 1/2. So distribute that exponent there. And then the only other thing I have left since I multiplied this negative 7 is I have x minus 4 squared in the bottom. And I'm going to go ahead and write that in there. Well, the thing is, since you have x minus 4 in the top and bottom, and they're both raised to exponents, you can simplify it to one thing. So we have negative 7 over 2 times, because the bigger exponent here, notice that they're both positive, which makes this a lot easier. The bigger exponent 2 is in the bottom, which means when we simplify this with this, it's going to be in the bottom. And all we do is we take this away if we subtract the 1/2 exponent from there. So 2 minus 1/2, this is 4 over 2 minus 1 over 2 is 3 over 2. And what are we left with then? Well, we are left with 1 on the top here. And on the bottom, we still have the x plus 3 to the 1/2. And then we have x minus 4. And we just figured that exponent simplifies when it cancels out with that to the 3/2. And then it might also go one more step and just multiply these fractions. So you got negative 7 on the top and 2 times x plus 3 to the 1/2 times x minus 4 to the 3 halves. Okay, so like I said, just when I started this, the only thing I would personally do is just simplify by multiplying the -7. But in some ways, this is more simplified because if you have to do more stuff with it, if you have to do another derivative, then having to do the derivative of this is a little more complicated than having to do the derivative of this, because this thing has kind of 3 parts to it. You have x minus 4 and x plus 3, which is 2 parts, and then another x minus 4. This one really only has 2 parts to it, x plus 3 and x minus 4. All right. So I know this video is already past the normal 20-ish minute mark, which I like to stop at, but we only have one problem left, and this one should be a lot shorter. What I typically find is when you have to find the derivative and you have a composition of multiple trig functions, it can get a little overwhelming, especially if it was sine of x. I don't know, it seems like when you see the same one twice, kind of throws off the brain a little bit. But what I want to show you is as long as you take the idea that we've been doing the entire time, you'll be fine. All right, to start, why do we need to do the chain rule? Well, look at what's on the outside. The sine is on the outside, and the inside is the entire cosine of x. All right, so the thing is, if this was just cosine of x, of course, if the sine of x wasn't there, then we wouldn't have to use the chain rule at all, because it would just be derivative of cosine of x, and we have a formula for that. But because we have this other trig function, or even just another function in general, we have to use the chain rule. But if you write down the outside or inside, or just record it in your head, this shouldn't be too bad. So dy over dx, we do the derivative of the outside. What's the derivative of sine? That's just cosine. We leave the inside the same, so it's cosine of x. And then we multiply by the derivative of the inside, for the derivative of cosine of x. Okay, so just keep track. We've been doing exactly the same thing. It's just, I know when I was learning this stuff, for some reason, multiple trig functions like this always mess with my head. Break it down, indicate the outside or the inside until you get at least comfortable with it to where you don't feel like you have to do that. And then you pretty much got this to a point where you can solve it pretty easily, because cosine of x, yeah, that's not a nice function. You can't simplify it in any way at all. One thing that should be said is this is not cosine squared of x. So let's just go ahead and write that as a reminder. Cosine squared of x is cosine of x squared, which means you do cosine of x times cosine of x. This is very different from what we have here. So this does not equal cosine of x. I just want to throw that in there because if you have the cosine, it might look like multiplication, but remember this is function composition. It's very different. All right, but get away from that side note. The derivative of cosine of x is negative sine of x. And because the inside is just x, we don't need an extra rule. Now this is a fine answer. Typically people like to put negative signs in front when there's multiplication. And if you want to put the sine of x in front, you can. Just remember that this is one trig function all stuck together. Sine of x is not involved with it at all, so it's not going to go inside, it's not going to go in between or anything. It either stays behind or goes all the way in front. So I'm just going to leave it in the back. Doesn't really matter. I just want to put that negative sign in front. All right, so this section, I didn't necessarily feel like it was necessary to kind of summarize our derivative rules so far, because we basically took all our old derivative rules. We're just using them in a different way called this chain rule. But I do know the chain rule is challenging. That's why I focused only on doing the derivatives. I didn't want to worry about using the terms velocity, acceleration, equation of tangent lines. All that stuff is valid. I just wanted to make sure we practiced understanding how to do the chain rule. Right, and I will see you in the next section.